So hi, I'm Nicolas Kwarnek, and I'm going to present you how we use Seastar, the framework powering ScyllaDB, to build a video streaming testing framework. So I'm working at Broadpeak, a provider of video streaming solutions for ISPs and content providers. And my current focus is on the performance evaluation of video delivery systems. So our goal currently is to benchmark and load test Broadpeak video CDN solutions. So the kind of systems that we are considering is the following. We have tens of thousands of video players that are running on top of Android browsers, iOS devices that request video parts over HTTP 1.1, HTTPS, HTTP2 to a caching server, which is a high-performance server. And we want to perform those benchmarks efficiently. By this, I mean that we don't want to invest into additional hardware. We want to reuse existing commodity-off-the-shelf servers that are already available. So, for example, if we consider a production system, we may have several servers with some of them that are actually failover servers. So we can take these failover server out of the system temporarily, use them to benchmark the rest of the system, and configure them back into the original system. In our lab, we have multipurpose test servers that are available that we use for running the various products and that we can also use to run benchmarking tools. And this means that we cannot rely on specific FPGA or specific hardware that would be required to perform the benchmark. The scale that we want to achieve is in the range of tens to hundreds of gigabits networking traffic. Also, we want to run tens of thousands concurrent clients simultaneously. So the current solutions to this problem are the following. So for Dash and HLS over HTTP, we are offered basically two main choices. The first is Apache Demeter, the open source, which can target in the range of 10 to 20 gigabits per second. It's great, it's open, it can be extended. However, one issue is that each simulated client corresponds to one thread. This has an impact on its performance. And also, it's not effective because we cannot pile 10 servers to test just one. That wouldn't be effective and that would be hard to test. So we are also offered commercial hardware appliances that can target in the range of 20 to 100 gigabits per second, depending on the protocol and on the appliance that we use. And those are high performance, which is great. However, they cannot be moved or replicated. By replicated, I mean that we cannot replicate them infinitely and have one of them for each team, each developer, and they cannot be moved, which means that the test must be performed into our premises, in Rennes, in France. We cannot perform the test on the customer premises on the specific hardware setup of a given customer. And finally, one issue is that there is a delay in the streaming protocol evolution and the availability of the latest feature for testing. And so this precludes us from testing, for example, low latency and the various latest development that we are currently doing. So what we did is the following. So we picked Seastar as a basis. So why Seastar? It's because actually our benchmarking application is IO intensive. It will be mostly doing receive and send over the network. So it's also a very good fit for the Seastar DPDK stack. And the second thing has to do with the number of clients that we want to emulate. So we were talking about tens of thousands concurrent clients, which means that we will have a very high concurrency level. And that's a good fit for the asynchronous model of Seastar. The second thing that we use is Chromium, actually, the widely used browser. And from Chromium, we get a full HTTP protocol support, HTTPS 1.1, HTTP2, HTTP3, compression, connection pooling, and so on. And so this is really instrumental to our highly realistic client emulation. This means that we have a very compliant protocol, HTTP protocol implementation. And the last thing is that on top of this, we implement a HLS and Dash player emulation. We leverage Seastar and the one thread per core model for this implementation to be highly efficient. And we use coroutines, we use Ragel for protocol parsing, as is done with Seastar. And also, what's important here is that we support the latest protocol evolution, like low latency, which was released last year, and Dash templates, all Dash templates. why did we choose Seastar rather than some other tool based on DPDK? Actually, we use Seastar because its full TCP stack runs very well into our benchmark with just minor fixes. And the socket-like abstraction that is offered on top of that stack allows us to implement complex applications like actually video players. And so the other point is that the asynchronous model of Seastar is a good fit for our video application. So it's a complex benchmarking application where we run thousands of concurrent video players, and each video player must schedule its video part downloads, periodic tasks like manifest update, where manifests are actually the list of available video parts. We must also simulate video buffer draining, timeouts, and so on. And finally, it also allows us to implement constant rate scheduling for avoiding coordinated omission. So Seastar is a great fit for our application, and it has only some minor issues. So what are these issues for the kind of application that we target? The kind of application that we target is a benchmarking application. So this means that it's really network IO intensive. We don't do any access to the disk. We don't read or write files. So what we observed is that Seastar periodically yields the CPU to the kernel precisely for handling files or timers. And so this has an impact on performance in our case. And so we fixed that by getting rid of the context switches for a pure networking benchmark application. And this has allowed us to boost the performance of our benchmarking application. The second thing is that Seastar has a native networking stack that has some limits. One of the limits is that it supports only a single NIC, and the other limit, or let's say designed limitation, is that it's designed first for server applications. So by this, I mean that we have a client that connects to a Seastar-based server. And so the network connection to core mapping is done through RSS, which is receive side scaling, which is a feature of network interface card, which is designed precisely for server application. And it's a good fit for Seastar receive connection. However, when Seastar initiates a connection, it's not so great. So what we did is that we implement a new multi-NIC packet steering mechanism for Seastar initiated connection and beyond. So let's review first how Seastar works currently. So Seastar native networking stack works in the following way. The Seastar application will expose a single IP address and MAC address to the network, and each CPU core will get its own receive queue on the physical NIC. So in the example here, I have 7 CPU, and hence I have 7 queues on the physical NIC. And whenever a packet is received, especially if it's the first packet of a connection, it will go through RSS hashing, which will dispatch the packet to one of the queue. And all the packets of the same connection will go through that queue in the rest of the processing. And so we see that it's great for server-side application, but for client-side, what Seastar does is that it kind of reverse the hashing by trying to pick a port that will ensure that traffic will come back to the right core. So what we did with Broadpeak sharding to the core networking stack is different. So we decided to expose each CPU core onto the network. So we give each CPU core its own identity, its own IP and MAC address, by giving each CPU core a dedicated virtual NIC. This virtual NIC can be VirtIO, Intel VMDQ, SRIOV devices, and so on. And so we see that this ensures that whenever a CPU initiates a connection or receives a connection, the packets naturally go to it because it has a dedicated IP and MAC address. And so we bind all those virtual NICs to the physical NIC to ensure that we don't require more hardware by doing this. And so you see that one benefit of this actually is that it allows us to support multiple physical NIC naturally. So rather than binding all virtual NICs to a single physical NIC, we can bind them to multiple physical NICs. That doesn't change anything. So it's quite flexible, and it allows to support multiple NICs. So here, what is great is that it works well for client application that can use multiple IP and MAC addresses. And actually, it can also be useful for server application in which the clients that connect to that server are actually shard aware and may want to contact a specific CPU which is responsible for a given shard. So if that's not the case of the application that you have, and you need to go back to a model where you have a single IP address to contact your server, then you can have the following scheme. So we'll leverage IP routing in the top of rack switch. So in the example I display here, the server can be contacted using a single IP address. The top of rack switch will perform ECMP hashing, which is the equivalent in the top of rack switches of RSS in the physical NIC. And this will dispatch the traffic onto the multiple physical NIC and onto the multiple CPU core of the Seastar application. So we see that this allows to implement a kind of link aggregation, but using IP routing, which is more convenient in particular in virtualization environment. So overall, to conclude this talk, so we've been able to use Seastar for an HTTP benchmarking tool, which is not a database or a server kind application. And it's been very efficient for this. And especially it has allowed us to implement a benchmarking tool that has kind of Gmeter-like capabilities with high flexibility, but with high performance levels. And it's currently in use at Broadpeak for testing and benchmarking. And this was with vanilla Seastar with just minor change to the core Seastar. We just required to consider how to use multiple NICs and how to handle reverse traffic for this. So if you are interested in this and you want to have more information, you can have a look at Chrononat, which was published at the Usenix ATC 2018, since what I presented is actually the implementation of some of the principles described there. So thanks for your attention. And if you want to contact me, you can contact me at those addresses.